Is it time to retire the metal sill pan? Let me begin by stating something that should be pretty obvious. There are lots of good ways of detailing windows, and there are lots of good materials we can use to that end. But there's one common approach to detailing windows that I really think is time to retire, and that is the metal sill pan. Let's see if I can persuade you. First, what is a metal sill pan, and why do we use it when detailing windows? Metal sill pan looks approximately like this. It's a shape we make out of metal. Usually we make it out of a single flat sheet of metal that we cut and bend into this shape. The parts that we bend are obviously continuous and watertight, but the parts that we cut obviously are not. We usually smear these metal to metal joints with sealant, or we solder them to make them watertight. What we're left with is a pan of sorts with a back dam, 2 end dams, and a drip edge. We place the pan into the bottom of framed openings before installing windows. Sometimes if our window is flanged, we won't have that angled drip edge. That outermost bend in the metal will just sit flat, flush with the sheathing. The purpose of the metal pan flashing is to protect the framed opening at the sill from water damage from a leaking window. This is a really important distinction to make. This is about the opening, the window to wall interface, not the window itself. If windows didn't leak, we would not need to protect the framing from water damage. But windows do leak, and it's silly and unproductive to pretend otherwise. Window manufacturers, even of high-performance, expensive windows, don't actually claim that their windows don't leak, at least not formally. What they claim, accurately, is that their windows meet certain water holdout performance criteria when tested in a laboratory. And that is a very different claim. Windows have a lot of complicated internal joinery that's difficult to seal even in factory conditions. And this same joinery can get stressed during transport to the job site and also during the actual installation of the window into the rough opening. Even after the window has been installed, it sees a lot of abuse in service. It'll be exposed to wind, rain, UV, birds. It's not unreasonable to anticipate that any one of these things would cause a window to leak. And that's just the window itself. The window to wall interface can also leak. Windows are installed by real people who don't always do their work absolutely perfectly. We're installing windows in openings that aren't framed perfectly, using materials and methods that are sometimes a bit unfamiliar to us, in conditions that are sometimes difficult and unpleasant, like wind and rain. And even when we get that window to wall detail right, what are the odds that it will remain perfect throughout its entire service life? A service life that, let's be honest, never looks quite like the laboratory conditions that we tested the window to originally. The best details and the best architects anticipate all of this. They don't depend on perfection in the manufacture, installation, or maintenance of the window, or in the environment to which it's exposed. A foolish architect asks, how can I design a window that doesn't leak? A wise architect asks, under what conditions will this window leak? And is there anything I can do about those conditions? How can I reduce the consequences of a leak? Protecting the moisture-sensitive framing and cavity insulation below and around a window is one of the ways we respond appropriately and responsibly to window detailing. As you might imagine, the highest risk spot for us to protect is the sill, hence the metal sill pan. It's worth noting here that the building code currently only requires protecting the openings into which we install windows at the sill, and the language about how we go about doing so is pretty liberal. Along the same lines, manufacturers, both of windows and of water control membranes, tend to stick with this minimal recommendation of protecting just the sill. This is fine as far as a minimum standard goes, but I recommend protecting the whole opening from water. While the sill is certainly the highest risk spot, the whole opening is vulnerable, especially the cut edges of the sheathing. As an aside, protecting the whole opening is also beneficial from an air control perspective. In North American construction, we're often using the water control membrane over the sheathing to also control air. Bringing that membrane to the interior on all four sides of every window opening facilitates continuity in our air control system. And that has all kinds of other efficiency and comfort benefits. But that's a bit beyond our scope today. Back to metal sill pans. Do they work? Yes, they've worked for a long time. But I submit that using a flexible membrane to form the shape is easier and less risky than forming the shape with metal. This is a complicated shape to form, and even when we do a reasonable job of it, it still has some pretty big drawbacks. For one, a metal sill pan will always be smaller than the opening into which we install it. It has to be, otherwise it wouldn't fit. The problem with that is that it is very common to forget to lap whatever we're doing at the jamb into the sill pan. It's very common to instead drain the jambs behind or under the metal sill pan, which of course defeats the purpose. A membrane sill pan, by contrast, tends to be more forgiving. We first install either a metal angle or a wood nailer into an opening at the sill to serve as a back dam. And then we use a membrane to form essentially the same shape as our metal pan flashing. The difference is it tends to be much easier to conform to the actual geometries of the opening with membrane rather than metal, and the jamb flashing and sill flashing can be continuous. Note that metal sill pans are often fabricated off-site. A metal angle back dam is an unbelievably easy shape to make, and it can be made on-site by taking a single piece of sheet metal, cutting it to the exact width of the opening, and bending it once. A wood nailer is similarly simple. The risk reduction by itself is worth it in my opinion. But if you need more reasons to like membrane sill pans, they also facilitate better air control continuity because when we install our interior air seal at the window, it's between the window frame and our membrane air barrier rather than the metal sill pan. We also get to eliminate one more thermal bridge. All this said, membrane sill pans are not magic. It is, of course, possible to install them poorly too, and there is no question that a competently installed metal sill pan is far superior to a poorly installed membrane sill pan. But I do think it's important to note here that there are a couple apparent drawbacks to membrane sill pans that are, in my estimation, exaggerated. The first is that the membranes we might select are incapable of spanning the small gaps in the framing. For example, the joints between the cut edges of the exterior sheathing and the wood studs. Before I ever saw fluid membrane used on a real project, that's exactly what I thought. I was comfortable with the use of self-adhered membranes. We use them to bridge these kinds of small gaps created by changes in substrate all the time. But intuitively, it just didn't seem like a fluid membrane could do that. I guess maybe I was thinking of like regular paint, but our modern fluid membranes are manufactured specifically for these types of applications, and they're great at spanning these types of small gaps. Depending on the fluid membrane you select, larger gaps often need to be pre-treated with a joint filler prior to applying the membrane. So yes, definitely something to pay attention to, but no, not an inherent flaw to that approach. It's also very easy to inspect the installation for continuity after the fact, and defects in need of repair are pretty obvious. A second popular apparent drawback is the idea that membranes are less durable than metal. And here again, I can see the intuitive appeal of a more traditional metal. A lot of high-end homes will specify copper sill pans, for example. They might also be specifying solid mahogany windows that they expect to last 100 years. So again, the appeal of metal is obvious. And that said, it's a little unfair to compare the performance of copper sill pans in historic buildings with copper sill pans in new buildings with modern HVAC systems. When we keep interior conditions to modern standards of comfort, the thermal bridging you get with a full metal sill pan is not so much an energy issue as it is a durability issue due to repeated wetting from condensation. It's perhaps also helpful to point out that on these same types of buildings, we routinely install Grace Ice and Water Shield under slate roofs or under copper roofs. We don't install 2 layers of copper. We're typically pretty comfortable using membranes and fluids in other parts of these buildings. And speaking of roofs, we can expect a service life of 20 to 25 years out of a typical EPDM roofing membrane that's fully exposed to UV and temperatures of 180 degrees Fahrenheit throughout its entire service life. So while we can't know for sure precisely how durable these membranes will turn out to be, I don't think it's unreasonable to expect a 100-year service life out of a fully adhered or fluid membrane installed at a window. These aren't moving joints, and whatever membrane we use will be protected from UV and extreme temperatures throughout its service life. In my estimation, the risk reduction and air performance benefits of membrane sill pans far outweighs the potential and perhaps only nominal long-term durability benefits of metal sill pans. But design is about trade-offs and everybody is different. I'd like to conclude by showing you a nice hybrid approach. This might help kind of split the difference in the kind of high-end residential or institutional projects we've just been talking about. But it's also an approach I really love for doors in all construction types. And the hybrid approach is this. Use a membrane sill pan that's continuous with the jamb flashing, just like we've discussed, but also apply a metal angle on top for impact resistance. This is particularly helpful at doors for obvious reasons, we step on them. But it can also be beneficial at windows where we might want to add a drip for increased durability and help with staining, for example. The metal angle edge protection should not be set in sealant though, at least not continuous sealant. We want drainage to occur freely underneath it. And it need not have end dams or a back dam. The one I'm showing you here has both. It certainly would have been my preference to omit these for better continuity in the air barrier, but I don't always get my way, and it's still a beautiful installation.